Alright guys, so in this video I wanted to talk about Pascal's triangle. Now before I talk about Pascal's triangle, I want to introduce you to just a little notation because I'll be using it in this video. Before I start this video, I just wanted to say if at any point this video doesn't make sense, you can go to Khan Academy. They have a lot of good videos and articles on this. Also, your school notes will probably be good sources of information for learning this. This video is just one way to look at this subject. Okay. So if I were to write 10 and then a C and then 2, that's the same thing as basically saying that I'm taking combinations by taking 2 elements out of a 10 element group. Okay. If I were to do P and then a 7 and then a 3, that's saying that I'm taking permutations of 3 elements out of a 7 element group. So that's just a little notation that I'll be using just to speed things up a bit. Okay. So first, before I talk about Pascal's triangle, I want to expand x plus y to the 4th. Okay. And when x plus y to the 4th is the same thing as x plus y times x plus y times x plus y times x plus y. Right? And there are going to be a certain number of terms that will be produced from this, right? And I'll write out the terms. So it'll be x to the 4th is the first term. So x to the 3rd times y plus x squared y squared, plus a certain amount of this. Plus 4x cubed y plus 6x squared y squared plus 4x y cubed plus y to the 4th. Okay. All right. So that's great, but where am I leading with this? Well, you might notice that this x to the 4th is a combination of 4 x's, right? This 4x cubed y, this x cubed y here is a combination of 3 x's and then 1 y. This over here is a combination of 2 x's, 2 y's. Okay? This over here is a combination of 1x, 3 y's. This over here is a combination of 4 y's. Okay? So based on which either x's or y's are picked from each factor here, from each x plus y over here, that will affect which ones are produced. So, for example, x times x times x times x would get you x to the 4th. And then if we were to pick 3 x's, so x times x times x, and then a y, we would get x cubed y. Okay? So each of these terms are products of different combinations of x's and y's. So you can have 4 x's, 3 x's, and 1 y, 2 x's, 2 y's, 1 x, 3 y's, or 4 y's in this case. And in a way, these coefficients represent the number of different ways 3 x's and 1 y can be chosen. And I'll show you what I mean by that. So each of these coefficients sort of represents the number of combinations that 3 x's and 1 y can be chosen. Okay, so what I mean by that, maybe this is an x that's chosen, this is an x that's chosen, then this is a y that's chosen, and then this is an x that's chosen. So that way we still have 3 x's and 1 y, just not in that particular order that we had before. Or maybe we would have a y here and an x here. So that's what I mean by that. Each of these different factors can either be a y or an x. So we can sort of pick which one they're going to be, and the number of different ways we can pick whether they're x's and y's, and they'll still produce a certain number of y's and x's will determine how many combinations there are for producing a certain tune, for producing maybe x cubed y, for example. So in this case, there are 4 combinations of picking 3 x's and then 1 y. Okay? So essentially, we're taking a certain number of x's and a certain number of y's for each one. And then these coefficients represent how many different ways those x's and y's can be chosen. So how would we actually calculate these combinations if we wanted to know the coefficient of some larger power of x plus y? Well, let's take x squared y squared, for example. We know x squared y squared has 2 x's, right? And x plus y is being multiplied by itself 4 times. Okay? So we have 4 of them. We have 4 x plus y's, and we know that 2 of them have to be x's, right? So essentially, to find out how many different ways we can take 2 x's out of these 4 x plus y's, how many different ways we can choose 2 of them to be x's, what we have to do is we have to basically find how many different ways we can choose 2 x's. Okay? So what I mean by that is we can sort of pretend like we're choosing 2 of these x plus y's to be x's. And we're finding out how many different ways we can choose 2 of them to be x's. And when we find out how many different ways we can choose 2 of them to be x's, that will be our coefficient. Okay? So we have 4 x plus y's, and we need to pick 2 of them to be x's. Okay? So how many different ways can we take 2 of these 4 x plus y's? So I'll draw the positions. Well, this first position can be 4 different x plus y's, right? It can be any of these. This could be an x, this could be an x, this could be an x, or this could be an x. So there will be 4 here, right? Now, this second position can be 3 different things, because it can be anything except for the first position, what the first position holds. So we get that there are 12 permutations for taking out 2 of these x plus y's and choosing them to be x's. But it doesn't really matter what order we take these x plus y's out, so we want combinations. So we're going to divide by 2 factorial, the number of positions factorial. So we get 6. And we can see that it actually worked out. It ended up being a 6. So basically what we're doing, what I just did, was I picked 2 of these x plus y's to be x's, okay? And I found out the number of ways I could pick out the different x plus y's to be x's. So what I mean okay, maybe this is x plus y sub 1, this is x plus y sub 2, this is x plus y sub 3, this is x plus y sub 4. Okay? I chose 2 of these to be x's, okay? In order to find out how many different combinations of 2 x's would be produced if they were being multiplied, right? Because essentially what's happening when these are being multiplied is everything is being multiplied with whatever it can be. So all combinations are being fulfilled, okay? So let's say we wanted 4x's. That will be fulfilled, right? Because we're getting an x to the fourth. X cubed y, so 3x's and 1y. That's being fulfilled. What I was doing there was I was just finding out how many different combinations there were of x squared y squared. So all I have to do is I have to find out how many different ways you can pick 2 of those x plus y's from this group. And finding out how many different ways you can pick 2 from that group of x plus y's gets you the number of x squared y squareds produced when they're multiplied together, okay? Because we know that there are going to be 2 x's in the x squared y squared, so we know that 2 of these must be chosen for being an x, and therefore the other 2 will automatically be y's. And then I found out the number of combinations, which is 6, to get our coefficient. Let's just do another one in case that was at all confusing. Don't worry, I'm getting to Pascal's triangle. Just want to really cement what I was just doing there. So let's say we have x plus y to the 5th. Okay? What is that going to end up being? Well, we are going to have x to the 5th plus some number, I don't know, I'll just use a, first letter of the alphabet, of x to the 4th y plus some number of x to the 3rd y squared plus some number of x squared y to the 3rd, right? Plus some number of x y to the 4th plus some number of just y to the 5th, right? So these variables all are just coefficients, okay? There are coefficients representing how many of these can be produced. And these coefficients we know will be the combination for picking each one. So maybe this x to the 4th y will just is a combination of 4 x's. So you had to pick 4 x's from this x plus y to the 5th. So 4 of those x plus y's were x's, and then 1 of them was a y, okay, in whatever order. You know what, just to make things really clear, write it all out, because I think it's pretty difficult to wrap your head around at first, at least it was for me. X plus y, okay? Okay. All right. Now, there are 5 x plus y's here, okay? When we're multiplying these together to form our terms, essentially what we're doing is we're picking either x or y from each of these x plus y's, and when we pick whatever number of x's or y's we got from this, whenever we pick that, it results in a term, okay? So let's say we picked x here, so x was being multiplied, and then y was being multiplied, and then x, and then y, and then another y. That would result in x squared y cubed, right? Sure, no, it's here, right? It's right here. And we can have a certain number of these x squared y cubes because these are not necessarily in the exact order all the time. So maybe this one will be an x, and then this one will be a y. So there are different combinations for which these can be picked for being x's or y's. Okay. But when we're multiplying these numbers together, all the combinations of x's and y's will be fulfilled when they're being multiplied together. It's just a question of how many of those can be produced. So x to the fifth is a certain combination, right? X, 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 x. If all of these are x's, then we get an x to the fifth. But there's only one way that can happen. It's if they're all x's. So thus we only have one x to the fifth. X to the fourth y. Well, there's only a certain number of ways that can happen. Yeah, and so on. So let's use our knowledge of knowing that the coefficients are just the number of combinations of ways that the x's and y's can be picked, right, to solve for one of these coefficients. So this right here, we know that there are going to be 2 x's and 3 y's. The next thing I want to clarify is why we can do what we do when we're taking our combinations. Because what I did last time is I basically said there are going to be 5 x plus y's, right? 5 x plus y's, and we're taking 2 x's out of this. We're choosing 2 of them. I said we're choosing 2 of them to be x's, okay? So we're choosing 2 of them to be x's. Now, why does this make sense? Why does this make sense when we're calculating the number of combinations? Well, I'll write out all the x plus y's. Okay. This one right over here. So we're basically choosing 2 of these to be x's, right? And we know the rest of them will be y's. So we want to know how many different ways 2 of these can be x's. Because in finding that out, we're basically finding out how many different ways 2 of them can be x's and 3 of them can be y's. Because we know if we find out the number of ways 2 of them can be x's, then that's the same as finding out how many different ways 2 x's, 2 of them will be x's and 3 of them will be y's. Because if 2 of them are x's, then we know that the other 3 will automatically be y's. Okay? So for example, if we were to choose this one and this one, whatever, there's some number of ways we can pick 2 of these, right? Then the other 3 would automatically be y's. So let's actually solve for this. So again, all we're doing is we're finding out how many different ways we can pluck out 2 of these x plus y's to find out how many different ways 2 of these can be x's. Okay? So we're pulling out 2 from the 5 of the x plus y's, right? So let's calculate that. Well, we basically have 2 positions because we're taking out 2 numbers, right? The first one can be any 5 of them, and the second one can only be 4. So we have 20 different permutations for picking these. Okay? Now, this is our number of permutations, but it doesn't really matter the order that we pluck these out. So we would divide by 2 factorial because there are 2 positions to get the number of combinations, which is 10. So there are 10 combinations for taking out 2 x plus y's, or in other words, there are 10 different ways, or that also means that there are 10 different ways that 2 of these can be x's. So that means that the coefficient c over here is 10. Okay? All right. Now, how does this tie in to Pascal's triangle? Well, Pascal's triangle looks something like this. Or at least part of it does. And you'll see what I mean in a second. But So this is Pascal's triangle, or part of it. And it sort of represents the different coefficients for x plus y to some power, or it can be used to represent that. That's not its sole purpose, but so this 1 over here represents x plus y to the 0 power, which is the same thing as 1, okay? So there's a coefficient here, and it's 1, right? Or I guess that can be thought of as a coefficient. And if we have x plus y to the 1 power, that's the same thing as x plus y. And there's a coefficient of 1, then there's a coefficient of 1, because we know that there's a 1 before the x and a 1 before the y. X plus y squared, maybe we're seeing the pattern now, is equal to x squared plus 2xy plus y squared. And we see that there's a coefficient of 1 here, coefficient of 2 here, a coefficient of 1 here. And we have a 1, a 2, and a 1 here. So that's sort of the correlation between Pascal's triangle and x plus y to some power. You might notice that this x plus y to the 5th here is actually going to be represented by this bottom row. 1, 5, 10, 10, and 5, and 1. So what does that mean? Well, it means that the coefficient here will be 1. The coefficient here will be this a right over here is 5. This b over here is 10. This c over here is 10. This d over here is 5. This e over here is 1. So you can see that it does work. This is represented, well, at least the coefficients in it are being represented by Pascal's triangle, or this row of Pascal's triangle. There are actually rows beneath this, you can imagine, and it goes on sort of forever, right? You can imagine. Okay. And this would represent x plus y to the 6th, right? This is x plus y to the 5th, you know. And it would go on for all of the x plus y to some power, right? So each row would correspond to a different set of coefficients for x plus y to some power. So the first row represents x plus y to the 0, second row x plus y to the 1, third row represents the coefficients for x plus y squared, and then as it goes on, it goes on for however many x plus y to some power. So you can imagine the 100th row would represent x plus y to the 99th. So every single row would represent x plus y to a different power. So because the first row represents x plus y to the 0 power, the second row would represent x plus y to the 1st power, and so on. Now I want to talk about combinations that we can, well, I want to relate combinations to Pascal's triangle. So yeah, so we're going to look at another way to look at Pascal's triangle using combinations to sort of represent each coefficient. And hopefully you'll see what I mean right now in a second. So these numbers, they represent the coefficients, right? And if they represent the coefficients, that means that they also represent the number of combinations of ways certain things can happen, right? So I said I would use the notation, so I'll write it out and then I'll explain what I'm doing. So this represents 0, choosing 0, right, for combinations. This represents having a group of 1 and then you're choosing nothing. This represents having a group of 1, then you're choosing 1. I suggest you get comfortable with this notation before moving on, because I won't be slowing down much, but you can pause the video and just get comfortable with this notation, because it can be a bit confusing if you aren't comfortable with the notation. But yeah. Okay, that's as far as I'll go. But remember, these represent taking out a certain number of elements from a group of elements. Oh shoot, this is not meant to be. This is a 0. But just to refresh your minds, from the beginning of the video, I said, like, 2 choose 1. I'll just say 2 choose 1 to represent this. That's the same thing as having a group of 2 elements, and then you're seeing how many combinations there are for taking out one of those elements. Okay? Yeah. All right. So how does this all relate? Well, like I said, these represent coefficients, which means that they represent combinations, right? Because we talked about why the coefficients are basically combinations for picking different numbers of x's and y's. So for example, this coefficient right over here, 10, is basically the number of combinations that you can pick out 2 x's and 3 y's from this group of 5 x's plus y's. Okay? All right, so you can see why all of these combinations relate to these. So 0 choose 0 is the same thing as 1. It equates to 1. 1 choose 0 and 1 choose 1 is the same thing as 1, 1, and so on, right? They're all equal to each other, right? The numbers that they correspond to. So for example, this number right over here, 3 choosing 2, so a group of 3 elements choosing 2 elements, the number of combinations is equal to, well, let's see, 1, 2, 3, 4. So 3 would be equal to this number over here, 3, right? Now, why is it that all of these combinations are in the order that they are? So why is 0 choose 0 at the top, 1 choose 0, then 1 choose 1 in the second row, and so on? Why is that? Well, we can imagine we're just taking combinations and we're finding out what they equal to get our coefficients, right? So for example, if we looked at 2 choose 1, so on the third row in the middle, we're basically saying that we want to find out how many different combinations there are for taking one element out of a 2-element group. So you can imagine, just like we were taking x out of 1x out of or finding out how many different ways you can take out a certain number of x's out of a certain number of x plus y's. So choosing a certain amount of those x plus y's to be x's. 2 choose 1 is basically saying there are 2 x plus y's, and we want to choose one of those to be x's. So how many different ways are there for that to happen? And it turns out there are 2. And because there are 2, the coefficient for x times y is 2. Because there are 2 different ways to pick one x out of 2 x plus y group. So basically we can pick either one to be the x, the other one will be the y, and there are 2 ways to do that. So there are 2 possible ways to get x times y out of x plus y being multiplied by itself once. So there are 2 x plus y's. We're finding out how to take out 1x, and that's the combinations. So the combinations for picking the number of ways we can pick out just 1x out of 2 x plus y's. So we're picking one of those x plus y's to be an x. There are 2 different ways to do that. You can either pick the first x plus y to be an x or the second x plus y to be an x. So therefore, there are 2 ways to get x times y. So that's why the coefficient is 2. So because 2 choose 1 is equal to 2, the coefficient for x times y is 2. So hopefully that you can see that really we're just rewriting all of these numbers. So for example, the 2, we're just writing it as 2 choose 1 because 2 choose 1, the number of combinations that you get from plucking one element out of a 2-element group equals 2. So we're just writing it with the combinations to kind of show the connection between Pascal's triangle and combinations. Now, for example, let's do another one. The 3 choose 2 at the bottom of Pascal's triangle on the left, that's equivalent to 4. So the 4 is equal to the number of combinations you would get if you were to find how many combinations you could get from choosing 2 elements from a 3-element group. So the number of combinations you can get from choosing 2 elements out of a 3-element group is equal to 4. Yeah. And something worth noting is that these combinations on the left, they don't all represent choosing a certain number of those factors to be x. They can also represent choosing a number of those factors to be y. So for example, the 3 sub 2 on the 3 choose 2 on the bottom represents choosing 2 elements out of a 3-element group. So we know that we're choosing 2x plus y's out of 3x plus y's, right? Now, that can mean two things. That's the same thing as two things. That's the same thing as picking 2 of those x plus y's to be x, but it's also the same as picking 2 of those x plus y's to be y. So the coefficient of 4, which is the number of combinations you get from choosing 2 elements out of a 3-element group, is the coefficient for both x times y squared and x squared times y. So they both have the same number of coefficients because choosing 2 y's out of 3x plus y's, so choosing 2 of those x plus y's to be y's, and choosing 2 of those x plus y's to be x's, results in the same number of combinations. There's the same number of combinations for doing both. Because think, they're both equal to just picking 2 of those x plus y's out of that 3x plus y group. Yeah. And for example, the 3 choose 2, and just to recap, the 3 choose 2 actually in Pascal's triangle is used to represent x times y squared. So you're basically picking 2 x plus y's to be y. So it's not like we did before. We're actually, in this case, we are assuming that the ones that we take out are y's. Okay. Yeah. So again, we are basically out of a 3x plus y group, we're choosing 2 of those x plus y's to be y's. So the 3 choose 2 can be thought of as a coefficient for both x squared y as well as xy squared. Yeah, so yeah. And that's part of the reason why Pascal's triangle is symmetrical. In the example that I'm using now, I'm basically just saying that the number of combinations for picking 2 x's, for choosing 2x plus y's out of a 3x plus y group to be x's is the same as picking 2 x plus y's out of a 3x plus y group to be y's. So the number of combinations to produce x squared y is the same thing as is equal to the number of combinations for getting x times y squared. Yeah. And you can see, like, again, with the 3 choose 1, for example, that equals 3. So that 3 could be used to represent either the coefficient for the x squared times y or the x times y squared. It doesn't really matter because they're both equal. So Pascal's triangle, you can choose whether the left side is used for the terms where there are more x's, or whether the left side is used for the term with more y's. It doesn't really matter because Pascal's triangle is symmetrical. Yeah, so we can also represent Pascal's triangle with all of these combinations. But yeah, so we can also represent Pascal's triangle like this. It's the same thing, except we're not using just numbers, we're writing it as combination 4. Yeah. Okay. Now an interesting thing about Pascal's triangle is that for any number, the two numbers above it, if it has numbers above it, will add up to equal it. So, for example, this 3 over here, it has a 2 and a 1 beside it, or above it, sorry. 2 plus 1 equals 3. So any two numbers above another number will add together to equal that. Now, why does this make sense? Or why should this make intuitive sense? Well, when we have our x plus y to some power, z, right? And we're multiplying it by itself some number of times. Every time we multiply by itself, every term sort of has potential to multiply into something else. So that's a bit confusing, but I'll actually use an example just to clarify. Okay, let's say we have x plus y, and then we have x squared plus y plus xy plus y squared, right? Sorry, 2xy. I should really be using this Pascal's triangle, right? Because it gives me all of the coefficients. But anyways, we have x cubed plus 3x squared y plus 3xy squared plus y cubed, right? And so on, right? But when we're multiplying these as they go on, this third one is basically equal to this multiplied by x plus y, right? So this thing times x plus y will equal this, okay? Right? Because that makes sense, because this is basically x plus y squared, this is x plus y cubed, so all we have to do is multiply this by x plus y to equal this, okay? Now, each of these terms has certain potential to multiply into something else, okay? So for example, this x squared over here has the potential to be multiplied by either the x or the y, right? So it can be multiplied by the x to get the x cubed, or it can be multiplied by the y to get the to get one of the x squared y's, right? So I'll look for it on our Pascal's triangle. This one represents the coefficient for x squared, right? So it can either be multiplied by x squared, so it can be multiplied by x squared, right? Or sorry, it can be multiplied by x. It can be multiplied by x to get x to the third, right? This is x to the third. It represents the coefficient for x to the third. Or it can be multiplied by y to get one of the x squared y's. So there's a number of ways to get the x squared y's. This is just one of them, is for this x squared to be multiplied by the y. Another way for an x squared, or for x squared y's to be produced, is for this over here, and this 2 represents the 2xy, so it represents the xy. I won't write the 2 because it's right there. But this xy can be multiplied by x to produce 2 of the x squared y's, okay? If that makes any sense. This 2xy can be multiplied by x to equal 2x squared y, okay? Now we get the other x squared y, right? Because we know that we have 3 of these x squared y's from the x squared being multiplied by the y, which will just produce 1 x squared y. Okay? So in total we get 3. So we can add those together because the two numbers above one number represent the coefficients for the numbers that have potential to produce that number, or to produce the number that is the coefficient of. So that was a bit confusing probably to listen to. Let me just do it again for another example, just to clarify. So let's look at this this 4 over here. Okay, this 4 is being used to represent I think it's xy cubed. I think it's xy cubed. I'm pretty sure. So it's being used to represent xy cubed. This 3 is being used to represent xy squared, I think. Okay. Now this can be multiplied by a y to get 3xy squared, right? Because we know that if this is multiplied, right, because if this whole thing is being multiplied by x plus y to get the term below it, or to get x plus y to the 4th, right, this will be multiplied by y to produce xy cubed. This 1 over here represents the coefficient for y cubed, right? And if y cubed is multiplied by an x, then it will produce one of the xy cubes, right? One of the xy cubes possible. And obviously well, maybe not so obviously, there are 4 xy cubes that are produced from that. 3 of them are from the xy squared being multiplied by y. There are 3 of them, right? 3 xy squareds being multiplied by a y, which will get 3 xy cubed. And then we get 1 xy cubed from this y cubed being multiplied by x. So again, just to clarify, for every single number, or for every number with 2 numbers above it, so for example this 10, the 4 and the 6 represent coefficients of numbers, or of terms, that have the potential, if they were multiplied by x plus y, to produce the number that this coefficient is of. So this coefficient would be representing the coefficient of some term. This coefficient's term has the potential to multiply by something to turn into this term. And that's why you add these two together, because they both have potential to turn into that term. So you add them together because together that will get how many of those are produced. And actually, I'll just do one more, just in case the first 2 examples were a little too messy. And I'll take my time with this one. So okay. I'm pretty sure this is x plus y to the 5th. So I'll compare x plus y to the 5th and x plus y to the 6th. Okay. So x plus y to the 5th is x to the 5th plus 5x to the 4th times y plus 10 x to the 3rd times y squared plus 10 x squared y cubed plus 5 x y to the 4th plus y to the 5th, right? X plus y to the 6th is x to the 6th plus 6 x to the 5th y plus 15 x to the 4th y squared plus 20 x to the 3, x cubed times y to the 3, plus 15 x squared y to the 4th, plus 6 x y to the 5th, plus y to the 6th. Okay, wow, that was a lot of writing. But anyways, if we multiply this by x plus y, if we multiply it by that, multiply this thing by x plus y, this expression by x plus y, then we're going to get this expression, right? So each of these terms is going to be multiplied by x and y once, right? So for example, x to the 5th will be multiplied by x to produce x to the 6th, and then it will also be multiplied by y to produce one of the x to the 5th y's, right? For example, and another example would be 5x to the 4th times y will be multiplied by x to produce 5 of the x to the 5th y's, and also 5 of the x, and then will be multiplied by y to produce 5 of the x to the 4th y squareds. So let's show it on the Pascal's triangle. Okay. Let's look at these two 10s producing a 20. Why do they get to be added together to produce this 20, right? Why does that work? Well, this 10x cubed times y squared has the potential to multiply by an x or by a y. So let's look at what happens when it multiplies by the x. When it multiplies by the x, well, we're going to get 10x cubed y squared times x, which is equal to 10x to the 4th y squared, okay? So now if we look for the x to the 4th y squared, it turns out this 10x to the 4th times y squared works to produce 10x to the 4th y squareds when it's multiplied by x. What happens when it's multiplied by the y? Well, when it's multiplied by the y, it's going to produce 10x cubed y cubed, okay? That's what it's going to produce. This one, on the other hand, so we did this one already, so I'll do a check mark. This one over here, 10x squared y cubed, what's going to happen when it's multiplied by y? Well, it's going to produce 10x squared y to the 4th. So it's going to work to produce 10 of the x squared y to the 4ths. And that its coefficient is represented over here. So 15 are produced in total, but 10 of them are from this, this number over here. What happens when it's multiplied by x? Well, when it's multiplied by x, we get 10x cubed y cubed, okay? So it is also going to produce 10x cubed y cubed, like the number beside it. And that, if they both produce the same, the same x cubed y cubed, then that means that you would combine them. So you add them together to produce this 20. So because these both have the potential to produce x cubed y cubed, which its coefficient is being represented by this, they were placed beside each other, okay, so that they would be added together to produce this 20. Because they both have potential to produce x cubed y cubed, so they both contribute towards this 20 over here. And the same goes for all of the other numbers that are being added together to go and produce the number below them. Okay, so that pretty much concludes this video on Pascal's triangle. Yeah, so thank you.